In this topic, we will discuss about synchronous protocol and it's one of the division called character oriented protocol. Hello, let's talk about synchronous protocol. The speed of synchronous transmission make it the better choice over asynchronous transmission for both LAN, MAN, WAN technology. LAN means local area network, MAN means metropolitan area network, WAN means wide area network. Protocols governing synchronous transmission can be divided into two classes: character oriented protocol and bit oriented protocol. As we said, synchronous protocol is divided into character oriented protocol and bit oriented protocol. Character oriented protocol. Character oriented protocol is also called as byte oriented protocol. In character oriented protocol, data will transfer character by character. Interrupt a transition frame or a packet as a succession of characters, each usually composed of one byte. One byte means 8 bits. All control information is in the form of an existing character encoding. Example: ASCII characters. Okay, and bit oriented protocol. Bit oriented protocol interrupts a transmission frame or a packet as a succession of individual bits made by meaningful by the placement in the frame and by the with other bits. Control information in a bit oriented protocol can be one or multiple bit depending on the information embodied in the pattern. In a character-oriented protocol, the frame or packet is interrupted as a series of characters. In a bit-oriented protocol, the frame or packet is interrupted as a series of bits. For reasons we will examine later on this section, the character-oriented protocols are not efficient as a bit-oriented protocols and therefore now seldom used. They are, however, is easy to comprehend and employ the same logic and organization as a bit-oriented protocols. An understanding of character-oriented protocols provide an essential foundation for examination of bit-oriented protocol. In all data link protocols, that controls information is inserted into a data stream either as a separate control frame or as a additional to existing data frames. In character-oriented discipline, flowchart and error control of several existing character-oriented protocols, the best known as IBM's binary synchronous communication. Binary synchronous communication, also known as BSC, is a popular character oriented data link protocol developed by IBM in 1964. Unable to both point to point multi point configuration, it supports half duplex transmission using stop and wait ARQ flow controls and error correction. BSC does not support full duplex transmission or sliding window protocol. A popular character-oriented data link protocol is binary synchronous communication (BSC), which is specified half duplex transmission with stop and wait ARQ. I was developed by IBM. The table is a list of standard control character used in a BSC frame. Note that the character ACK is not used in this protocol. Remember, the BSC uses stop and wait ARQ Acknowledgements must be either ACK0 or ACK1 to specify alternating data frames. The characters in table are represented differently in different coding systems. Often they must be represented by two or three characters. The ASCII codes are also shown in the table. For a complete list of ASCII code, the BSC protocol divides a transmission into frames. If a frame is used strictly for control purpose, it is called control frame. Control frame are used to exchange information between communicating device. For example, to establish the initial connection to the control flow of transmission, to request error correction and to disconnect the device at the close of section. If a frame contains part or all the message data itself, it's called data frame. Data frame are used to transmit information but may also contain control information application to the information see in figure. The arrow shows the direction of transmission. The frame begins with two or more synchronization SYN character. This character alerts the receiver to arrival of a new frame and provide a bit pattern used by the receiving device to synchronize its timing with that of sending device. In this page, we will discover that ASCII for SYN is 00101110. The leading bit of byte is usually filled out by an additional 0. Two SYN characters together look like this: 00101100010110. After two synchronization character comes to start text character. This character signal receive the control information is ending and the next byte will be the data. Data or text consists of varying number of characters. End of the text character indicate the transmission between text and more control character. Finally, one or two characters called the block check count (BCC) are included for an error detecting. A BCC field can be one character longitude reducing check or two character cyclic redundancy check. A frame as a symbol as the one described above seldom useful. Usually we need to include the address of receiving device, the address of sending device and identifying the number of frame. For stop and wait ARQ, the information is included in specified field called header, which before XTX character everything received after SOH field, but before XTX character is headed information. The probability of an error in the block of text increases with the length of the frame. The more bits in a frame, the greater the likelihood that one of them will be corrupted in transit, and the great likelihood that change in several bits will cancel each other out and make the detection difficult. For the reason, text in a message is often divided between several blocks. Each block except the last one start with an XTX character and end with an intermediate text block. The last block start with an XTS but end with an ETS. Immediately after each ITB or ETS, a BCC field is sent. In a way, the receiver can check each block separately for errors, thereby increase the likelihood of detection. If an block contains an error, however, the entire frame must be retransmitted. After the ETS has been reached and the last BCC checked, The receiver sends single acknowledgement for the entire frame. See in a figure. Show the structure of multi-block frame. The example includes two blocks, but actual frame can move more than two. In the example explored above, a single frame carries an entire message. After each frame, the message is complete and the control of line passes to the secondary device. Some message, however, may be too long to fit into a format of a single frame. In such case, the sender can split the message not only among blocks but among frames. Several frames can carry continuations of a single message to let the receiver know the end of the frame is not the end of the transmission. The ETS character in all frame but last one is replaced by end of a transmission block. The receiver must be acknowledged each frame. The control frame serves three purposes: establish connections, maintaining flow and error control during data transmission, and terminating connections. A control frame should not be confused with a control character. A control frame is used by one device to send commands to or solicit information from another device. A control frame contain control character but no data. It carry information specific to functioning of data link layer shown in the basic format of BSC control frame. BSC was originally designed to transfer textual message. Today, however, a user is just as likely to want to send binary sequence that contain non-textual information and comments like programs and graphics. Unfortunately, message of this sort can create problem for BSC transmission. In the test field of a transmission includes an 8-bit pattern that look like BSC control character. The receiver interrupts it as one destroying sense of message. For example, a receiver the bit pattern 000011 read it as an ETX character. As we learned from the control frame above, whenever a receiver finds an ETX, it expects next two bits to BCC and being an error check. But the pattern 00011 here indeed as a data, not as a control information. Confusion between the control information and data is called lack of data transparency. Lack of data transparency. For a protocol to be useful, it must be a transparent. It must be able to carry any combination of bit as data without their being confused with control information. Data transparency in data communication, we should be able to send any combination of bits as a data. Data transparency in BSC is achieved by a process called byte stuffing. It involves two activities: being defining the transparent test region with data link escape DLE and presiding the DLE character within the transparency region by an DLE character. To define the transparent region, we insert one DLE character just before XTX character at the beginning of test field and another just being the ETX or ITB may contain control character, and to ignore them, the last DLE tells the receiver that transparent being has ended. Problems may still arise if the transparency region contains DLE characters test. In the case, we insert an additional DLE just before each DLE within the test. See in the figure shown as example of transparent frame.